Welcome to 5.4 Fundamental Theorem. Stop talking. Stop talking. Okay. So, we're going to continue on. 5.4 is the last lesson. As soon as we finish it today, wonderful. I'll give you the practice test. All right. I don't know if I put the solutions up. I'll double check after this. I also have the actual semester 2 final review for seniors. Now the idea was, we've been learning stuff, you took that week, reviewed everything that we've learned, and then we're going to learn a little more stuff, and then you'll review. So hopefully this spiral review will help you with your final. Ideally, everyone does really well on their final test. That's 15% of your grade. Awesome. Okay. Doesn't matter what your grade is. Everyone has to take it. Don't ask me. All right. Fundamental theorem of calculus. So, this is very important. Fundamental means important. So if f is continuous on an interval, then the function, why does this always go away? Big F of x is equal to the integral from a to x of small f of t dx. So this is little f of t. So notice this big f of t. This has a very specific meaning. It's an antiderivative. Big F of t is the antiderivative of small f of t. Cool. Because if you take okay, cool. I'm just going to say antiderivative. I know, it's been a hot second for some of us to do calc. Ideally, seniors, you've kept it up. I gave you some worksheets. On the lesson plan, I said they're due today. If you didn't turn them in, because I instructed Mr. Labita to take them from you if you're done, cool. Less paper for you to hold on to. If you were sick, missed a day, whatever, cool. Just give it to me by tomorrow. Tomorrow class, just bring it if you haven't already. Okay. So, keep in mind, if small f is continuous and big F of x is the antiderivative, that means big F has to be continuous everywhere as well. All right? That means big F has to have a derivative at every point. So, ready for the trick play of the day? If you take the derivative of your big F, you literally get back your small f. Now, notice the difference is all we did was we have it in terms of a different variable. That's all we're doing, in terms of a different variable. Okay. So I'm going to do an example.
So if you take the derivative of the antiderivative, you get the derivative.
You get back what you started with. Yep. What?
It's like I'm doing it.
More or less. It's kind of like undoing it. Exactly.
So there's not a second antiderivative?
Maybe wait 5-10 minutes and then see if that answers your question. Because I feel like it will answer your question by going through and showing you this. Okay, so a couple of things I want to make clear. This little a, this is a constant. It's just a number. I could put any number there. It doesn't matter. This is a constant. And then this x is a variable. So I'm taking an integral from a constant to a variable. Notice I have f of t dt, and at the end I end up with f of x. So literally all I'm doing is changing the variable. Okay, so the independent variables change. Otherwise, you get the same thing you started with. So I'm going to go through a little example. Okay, this is another way of writing it. Instead of saying, big F and little f, this is another way of writing it. If you see another textbook, this is also how they could show it to you, especially in college next year. All right, f of x is the integral from a to x of f prime of t dt. So literally, you're taking an integral, an antiderivative of a derivative, you get back your original function. Okay, so I'm going to do an example now. So if I have something like, okay, do you want me to use a different color or is it okay to use the same color? Different color it is. Okay, so let's say I'm taking the integral from 3 to x of t cubed dt. Okay, so I'm taking this integral. So remember, we're going over what the fundamental theorem of calculus is. It will make a little more sense in a sec. But let's go ahead and let's take the derivative of our antiderivative. We're going to take a derivative of an integral. Okay, so we're going to take a derivative of an integral. So, yeah. Okay, so what this literally is going to be is I'm going to take the derivative after I evaluate the integral. So remember, t cubed is the derivative of what function? Or how do you go backwards? If this is the derivative, how do you go back to the original function, right? Remember our power rule? You add 1 to the exponent and then divide by our new exponent. Do you remember the power rule? We went over this. I know, it's been like a week and a half. It's been a hot second. And then we're evaluating it from 3 to x. So I'm evaluating our definite integral because we have defined endpoints. So I'm evaluating it, and then once I have that evaluated, then I'll go through and I'll take the derivative. Right? So I'm going to go order of operations. I got d dx. I got to take the derivative at the end after I evaluate at my 2 endpoints. It's good? Is that what you're saying? You weren't talking. Okay. I don't know who was talking.
It is good.
Okay. That doesn't have to be it. Yes.
So I understand that like the antiderivative of 2 cubed is that one, but what makes the two things different? Does that make sense? Is that d over dx prime or no? Or is that or no?
Oh, you're talking about right here?
Yeah.
This thing, I don't know why it's not disappearing.
Oh, so you have to put a 0 there.
No. I was circling the little dot that wouldn't disappear.
So
now there's nothing there.
What differentiates them? How do you know which
Differentiates what? What are you talking about?
Like, how do you know which one's the antiderivative and which one's not?
Well, the integral and the dt,
Yeah.
integral means antiderivative. d dx is you're taking a derivative. If you have the integral, you're doing the opposite of taking a derivative. You're like untaking a derivative. That's why I see antiderivative.
Okay.
So here we're trying to take the derivative of an antiderivative. So it's almost like canceling out, but I hesitate to say this because it will like mess you up if you go to like one step further and have to use chain rule. So I'm hesitating to say totally undoing it because it's going to get harder. Okay, so after I evaluate this, right, so I'm taking the derivative. Let me evaluate the actual integral. So if I plug in, it's always the, what was I going to say? Oh, okay. It's always the upper bound minus the lower bound. Remember like evaluating these? So the upper bound is x, so I have x to the 4th over 4. Subtracting, and remember I'm evaluating 3 to the 4th over 4. Okay, let's go through and take the derivative. What is the derivative of x to the 4th over 4? What? We don't need to use quotient rule. It's like one term at a time. 4x to the 3rd over 4. And then what's the derivative of a constant? 0. So this turns out just to be x to the 3rd.
Wait, but really quick, the 4 underneath the x to the 4th, isn't that technically a constant?
It's 1/4 x to the 4th. It's a coefficient, not a constant. It's a coefficient.
So you've got to keep it together.
Yeah. Because if you have 1/4 x to the 3rd, this is the coefficient, versus if you just have 1/4, this whole term is a constant because it's just a number, versus this term, you have a coefficient of 1/4. What is the derivative of a constant of a number? 0. Because let's see, okay, this portion right here is from this guy. Okay, and then this is a constant. 3 to the 4th is 81 over 4. Derivative of 81 over 4 is just 0. Because there's no x associated with this. That's why it's 0. All right, perfect. What I want you to notice, I started out with a t cubed. I end up with a x cubed. All we did was change the independent variable. Okay, right? You're saying, what the heck? This isn't really different than what we did before. You're right. It's not that different. It just makes it a little more complicated. But I have to go through this because I've only been giving you nice integrals so far, and I need to give you some, like, you know, dirty, ugly ones for a sec. Okay, so is that everything I want to say about these? Yes. Okay. So next example, example 1, find dy dx. So what we're doing is we're trying to take the derivative of an integral, because notice y is the integral, blah, blah, blah. So if I want dy dx, that means I'm trying to take the derivative of an integral. Okay. with your right hand? No. Oh. Okay. When I say if you can't write, I have the solutions that are going to be posted. Okay. So, let's go step by step. So, I'm going to write this as, right, dy dx is equal to d dx of this whole integral, 0 to x, of 1 over 1 plus t squared dt. So I'm clearly being a little extra just on this first one because I want you to see every step. Eventually, like, you will be able to skip steps. Okay, so how you solve these is first you take the integral and then you take the derivative of what you found. So notice you're going to get the same function just with a new variable because I'm going from 0 to x. So if I evaluate this, literally all I'm going to get is the exact same function, right? 1 over 1 plus, but I changed my variable into an x squared. This is what the answer will be. Because notice, I'm going from 0 to x, a constant to a variable. Yes?
Sort of, so you only have to do one of them because since one of them is going to be constant.
Yep, and when you take the derivative of constant, it goes to 0. Mm-hmm. So keep in mind, my upper bound is just x. It's not x squared. It's not 1/2 x. It's not x cubed. It's literally just x right now. And the reason I'm telling you this is hinty hint, chain rule. We're going to have to deal with the chain rule soon, but not yet. Not quite. Just trying to get you in the mental headspace.
So the first step is to convert the t to x?
Yes, I'll say yes for that one because it's not always going to be in terms of t. We won't always be going in terms of x. It's because, okay,
it gives you dy over dz.
Right, so you're converting everything in terms of z.
1 over 1 plus z squared.
Well, if you're going from 0 to z. You have to look at your bounds, your upper and lower bounds.
Alrighty, I'll take your word.
Okay.
Oh, that's it? But we didn't do anything.
We did. Notice we started with a function with t, and now we ended up with an x. Our independent variable changed. And the reason we didn't do anything is because we're going from 0 to x. If we were going from 0 to x squared, there would be more stuff, right? We haven't, x is the simplest. What's the derivative of x? 1. All right, so we're good.
Oh my god.
Right? We gotta walk before we can run, okay? Gotta walk first.
So it's simple because we're only going from
because I'm giving you baby problems, ready? Baby food. Haven't given you a steak to chew yet, all right? We gotta do the baby food first. Next. I feel called out. That's the whole reason I can never be like a vegetarian. Till you have steaks in Nebraska. These people are like, oh, this is the best burger in Memphis. I was like, this is trash. I'm so mad. Why'd I waste my money there?
Burgers in Memphis? Don't they get like ribs and stuff?
I did go and get ribs.
Did you get fried pickles? Yeah, fried pickles.
Did you go to Gus's?
Fried okra?
You should have went our year. I think you agree.
I just love the Southwest. So I love the senior trip so much. It's so great. There's so much more free time. I'm not.
You like the senior trip one?
Well, it's different. It's because like you have more space and you're at the same hotel the whole time. So
see, that's nice.
I
love moving with so much fun. Where are we gonna go
tonight? Okay, let's keep going. Okay, let's keep going. I know, I just realized that. Okay, so now that we did this, what is the, so ready, I'll take the integral of cosine, and then I'll have to go back and take the derivative. All we're doing is just changing the inside. Changing the independent variable, and that's it.
We're not actually taking the derivative, right?
Well, because you already know what the derivative. If you take the antiderivative and then turn back and then take the derivative, it's pretty much the same. It's the exact same, it's just you're changing the independent variable here. Because instead of being in terms of t, you plugged in an x. Yes.
I don't understand how.
Okay, I'm
you
over this
just
question.
thought of-
You gotta let make it snappy. We have a lot to do.
But
Gotta keep it
what happens
going.
If the integral isn't, what happens if the range isn't perfect? What if it's like X?
It has to be a constant on the bottom and a variable on the top. It has to be. That's it. Has to be. Okay. We're going to deal with, see, your question is going to be answered in part B because, oh my gosh, like, actually, no. Which number is it? B on example 3. I'm going to explain. What if you have variable on both? You can't do that. All right, using chain rule. Now let's take it up a notch. So I'm going from a constant 1 to x squared. Ooh, we got some trouble here. Okay. So hint, we're going to be using the chain rule. More or less, when the variable is different than x, if it's not just an x, if it's x squared, x cubed, blah, 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 you have to multiply by the derivative of the upper bound. Okay, so I'm going to write that out for you, but first, let's write this out. Okay, so I'm going from 1 to x squared of cosine t dt. So normally what we would do is we instead write this just in terms of the variable, right? In terms of the upper bound. So I would write, okay, this is just going to be cosine of x squared. But guess what? We have this thing here. It's not just an x, it's an x squared. So we have to use chain rule. What's the derivative of
2 cosine x.
Of x squared?
2x.
Times 2x.
Oh, chain.
Chain.
So is that only if we have an exponent?
So
Or
when
if
do we
what
do
if it's
this?
1 over x.
So when the variable is different from x, no, because remember we're taking the antiderivative, the integral, and then we're turning around and taking the derivative, aka, cool, we take the antiderivative of cosine, we go back and get sine, and then we take the derivative and we go back to cosine. Like,
So technically you're doing it for x too, but like it's 1.
I might need you to repeat that. I was not fully paying attention, so I'll make sure to write my thought.
Oh, okay, yeah.
Okay, so when our variable at the top, our upper bound, is different, it's not just an x, we have to multiply by the derivative of the upper bound.
Multiply by derivative of upper bound.
Yes. Okay, so I have that up there so you can read. So notice it's not 1 to x, it's 1 to x squared. So because we're not going from 1 to x, right, x squared is different than x, we have to multiply by the derivative of x squared, right, our upper bound. Derivative of x squared is just 2x. So therefore, it's going to be 2x times cosine of x squared. And notice I put parentheses. I'm taking cosine of x squared. It's not cosine of x being squared. It's cosine of x squared. Are you writing this down? Okay. So, this next one. Notice the top is not just x. The top is negative 2x. Okay, so we have to go through, take the derivative, multiply it out. Okay, so first, right, remember, if we're taking the derivative of an antiderivative, we'll get back more or less the function that we already had, right? So let me write this out nicely. D dx. I'm writing really large. I gotta zoom in a little bit. Okay. D dx of the integral from -3 to -2x of u cubed minus 5 du. Okay, so I'll get the function I started with. Instead of u's, I'll have x's. So I have to plug in a -2x everywhere where I saw a u. 2x cubed minus 5. And then I have to multiply by the derivative of my upper bound. The derivative of -2x is, I have to multiply by -2.
What? It's not -6?
So the derivative of -2x is -2. Okay, don't forget to distribute the 3 out, the cubed. Negative 2 times negative 2 times negative 2 is negative 8. X cubed minus 5, and then I have to multiply by my negative 2. So you end up with 16x cubed plus 10.
So there's derivative within antiderivative.
So it's because the directions are find dy dx. So I'm giving you the equation y equals this antiderivative.
Okay.
When we take the derivative of an antiderivative, more or less you get the same function back. It just changes the independent variable. So instead of having the function in terms of t, you have it in terms of x. Now the issue is, what if you're not just going from a constant to x, right? Here I'm going to negative 2x. That's not just x, there's a negative 2 in front. So then you have to use chain rule and multiply by the derivative of your upper bound. Then we're good. So negative 2 cubed is negative 8. X cubed is x cubed. You have to, well, because this is just rules of exponents. Negative 2x is being cubed. Okay, so we did two straightforward examples. We've done 2 where you have to use chain rule. Now we're about to do 2 where you, what? Straightforward? The first 2 were the straightforward ones. These last 2, chain rule, a little harder. Now we're going to kick it up another notch. So, notice, I give you a function, y equals blah, antiderivative. Right, an integral. We want to find the derivative. But notice the variable is the bottom, not the top. So how can I flip it?
Negative.
Exactly. Ready? That's the trick play here. Right? So I'm going to rewrite this. First, I'm going to rewrite this as y equals negative of integral. But I'll flip from 5 to x of 3t sine t dx dt. That's the hard part. That's the hard part. So this is just going to be negative 3x sine x. The hard part, flipping the bounds. Okay, so this is a little more straightforward. Kind of tricky because we got the variable on the bottom, but now we know how to move it to the top of my bounds. Okay, and now is where the fun begins. I'm going to kick it up even more. Yeah, ready? Okay. Gotta have some spirit. So we know how to deal with constant to variable in the upper bound. What if we have a variable on the bottom? Okay, cool, we just flip it, but, ooh, got 2 variables, right? Both my upper and my lower bounds are variables. Now, what? Yeah, because 2x and x squared are both variables. Can't deal with it. We only can have one variable as a limit to apply the fundamental theorem of calculus. So we must split it. Gotta split it. What? What's wrong? What's wrong? I'm trying to make this as straightforward as possible. Really walk you through it. So I'm going to split it. I'm going to go from 2x to 0 and then 0 to x squared. That way I have a constant as one of my bounds. So I'm going to rewrite this as 2x to 0 of e to the t dt plus 0 to 2x. I'm sorry, to x squared. I already did 2x. To x squared. E to the t dt. Ah, so you say I cannot have a variable on the bottom. So if I flip it, I can write it as a negative.
How do we know that 2x is before x squared?
It's the 2x is on bottom. We're going from bottom to top. So all I did from the first pink line to the second pink line was flip my upper lower bounds for the first one. So I put a negative out front.
Wow, it's crazy.
I mean, it is. Yeah, I was trying to like proper headspace.
And imagine not knowing what you're doing.
Imagine September. Imagine you in September, right? Internally screaming. It's fine. Like this is
screaming no.
like this. This is.
So much more confusing. You know what? I'm really trying not to cry. Like I was. I feel like this could be.
Well, right. So one of the hopes of last week was really solidify some foundational knowledge, right? Forcing you to review. Stop talking. No, come on. Having you review how to take a derivative 101, right? Really having you do chapter 3 again. Chapter 4, let's apply derivatives one more time. Let's really practice with them. Then I had you do some more integrals. Really trying to force you to really solidify those bottom foundationals, because man, if you don't understand those, it's rough. When I say, okay, what's the derivative of negative 2x? You gotta be like negative 2, right? You gotta have it. You can't be like, derivative, okay, so no. Gotta have it, right? By now, gotta have it, because, So ready? Chapter 3, learn how to take derivatives. Chapter 4, apply them. Chapter 5, learn about integrals. Chapter 6, apply them. And that's what we're doing before seniors leave. Okay, let's keep going. So what is the derivative of e to the t? E to the t. What's the integral of e to the t? E to the t. Okay, so, right, so it's going to be the same. So I'm going to write this as, so it's just going to be negative e to the 2x multiply derivative of 2x is 2. Okay, add. So e to the top bound x squared. What's the derivative of x squared? 2x.
Wait, whoa. So when you're doing the chain rule with the derivative with e to the power of something, you just bring that power down?
The derivative of the upper bound.
Yes.
Okay.
Wait, can you explain? I'm confused with how the bounds at the top. The 0, the 0 plus the 0 divided squared.
Okay, because if I would evaluate, so if I would go through this guy right here, right, evaluate it as a definite integral, you would get e to the, 2x minus 1 or whatever. You would get a constant. That's why I ignore the constant, because when I go back and then take the derivative, derivative of constant 0 goes away. So I'm only worried about the one with the variable. Yeah. And end up, yeah. Okay, so let me pull out a constant. It doesn't really matter. So I have negative 2e to the 2x plus 2x e to the x squared. This is it. This is my solution. All right, because we split it into 2 regions. This is how you deal with a variable on your upper and lower bound. So the next page is just 6 examples, more or less, you've already done. You did not realize, but you have been applying the fundamental theorem of calculus for a while now. Right? F of b minus f of a. The upper, all right, evaluate the upper minus the evaluation of the lower. We're gonna go through it. Okay.
Why are you subtracting them?
All right, are you on the next page?
Yeah.
Okay. So if f is continuous, right, or a little f, the thing we're taking the integral of, if it's continuous, that means f, and if f is any antiderivative of our small f, if the antiderivative is the antiderivative of our small f on our closed interval, what you can do to evaluate our antiderivative, you can just plug in your 2 endpoints into your antiderivative to actually evaluate the integral. We've done this. We have been doing this. This is from, no, we don't remember? Maybe? We've been doing this? Okay. No, I swear this wasn't a dream. I know we've been doing this already. Okay, so this line right here, in case you keep your notes for college or whatever, so to make it clear what other textbooks will show you it as, it will show you the integral from a to b of f prime of x dx, and this is just going to be f of b minus f of a, and this is the way my textbook showed it when I was first learning it. The fundamental theorem of calculus is fundamental, right? It is literally, it is very, very important. That's why we're spending a whole day on it.
Did you learn this in in college? Or
No, I learned it in high school.
In like 10th grade?
No. I didn't go to a fancy private school. So. I know. But like people who take, there are people I met who as like sophomores took calc BC. Like we didn't have APs in my school, so we like gotta take it when I can. Okay. So other books will show it this way. Notice you're taking the integral of a derivative, literally anti-deriving a derivative. Like you get back your original function. Okay. So this is called integral evaluation theorem. We had been doing this already. You just didn't know it. Evaluate it. Okay, ready? This is just like the worksheet you're working on right now. 4 is the derivative of what function, right? Like, how do I go backwards, right? You have to add 1 to your exponent. We're just going to use power rule. Add 1 to the exponent, divide by your new exponent. This is just going to be 4x plus, let's see, 2x squared over 2, and I'm evaluating at 4 and 6. Do you need me to back up and show you how I got this?
no.
Maybe a little? Okay. Okay. So secretly, this is 4 times x to the 0 power, because x to the 0 power is 1. So if I add 1 to the exponent, right, my new exponent is 1, and then I divide the whole thing by 1, I just end up with 4x. Okay, this is 2x to the first. So if I add 1 to the exponent, that's now x squared. I divide by my new exponent, which is 2. That's why I have 2x squared over 2.
So you find the antiderivative first.
Okay, and now I evaluate. It's always the upper minus the lower. So it's going to be 4 times 6 plus 2 times 6 squared over 2, upper, minus evaluating at the lower. Does it make sense what I mean when I say you've been doing this already? This is literally one of your worksheets right now. You just didn't know it was a fundamental theorem of calculus. And now I can throw harder problems at you. Right? I can.
But you love us, right?
Of course. I was just thinking, I was like, they're going to say, did you miss me? And I'll be like, yeah, I'll admit it this time. Yeah, see? A surprise.
Say it like you mean it.
I said it like I meant it before 1040. For the people who are here before 1040, I did. 24, 36, 72 over 2, 36 plus 24. I don't want to do that. 24 plus 36 minus 16. 4 squared is 16. Okay. Plus 6 minus 16? No, minus 32. Minus 32.
Oh.
Okay, so that's 28. I mean, you just type in your calculator, whatever. You can do the math. I trust you can compute using, order of operations. Let's try B. Okay, integral from -1 to e. Okay, what is e to the x is the derivative of what? Okay, so if you take the derivative of e to the x, you get e to the x, right? Cha-cha guy, remember? Take the integral of e to the x, still e to the x. What? Whatever. Okay, top minus bottom. Okay, upper minus lower. E to the e minus 1 over e. What?
So, why wouldn't you do like e to the x squared over 2?
E to the x squared over 2. Because this isn't x. Our base is not x. Our base is e. It's not a polynomial.
Oh, so then you just take.
Right. If this was x, and then it would be okay.
It was like x to the e. What?
We could do it. It's just like that's hard.
That'd be crazy.
Yeah.
So
It's
e to the x, which is
so the base is x. Power rule. If its base is
not
e,
you take the derivative.
yeah, e to the x. The derivative is always e to the x. E to the x. The integral is always e to the x.
And if it was like e to the 2x, it'd be 2.
That would be a little different.
It'd be 2e.
You have to use chain rule.
Oh yeah, so it'd be 2 times e to the x. 2 times e to the 2x.
2 times e to the 2x.
Nope.
It'd be 1/2 e to the 2x. Because when you take the derivative, it has to go back to e to the 2x.
Okay, but you still don't do like that.
No, because if notice I didn't give you a number in front of x right there.
This is Brian, how do you do like just regular derivative like e to the 2x? Do you do like
Regular.
it's like 2
So d dx of e to the 2x. So e to the 2x times 2.
Oh yeah, right.
Yeah, so wouldn't it be 2 to e to 2?
So if you're trying to take the if you take the integral of 1/2 e to the 2x, you'll get e to the 2x. This was your question. You're saying what if it was just e to the 2x?
Okay.
And the reason it's 1/2 is because if I take the, let's see, this is the derivative of this guy.
Yeah.
Because if you take 1/2 times 2 times e to the 2x, it goes to e to the 2x. Okay, let's go on. How about this boy? Hey, what about this one? Notice the base is an x. It is a polynomial. We're going to use the power rule. So we add 1 to the exponent, divide by our new exponent. So this is x to the 4th over 4. And then plus x. I'm evaluating it from -1 to 3.
Wait. So the antiderivative of 1 is x?
Yes, because what is the derivative of x? 1.
Well, 1 to the power of 1 over 1.
1 times x to the 0. So if you add 1 to the, because remember x to the 0 is just 1. X to the 0 is 1. Yep. So if I have x to the 0 and I add 1 on the top, add 1 to your exponent. If you have, yeah. Because if we go backwards, if I take the derivative of this, it should be here. The derivative of this should be what I started with.
But wouldn't that give you x to the 1 over 1?
Yeah, which is just x.
Which is x? Okay.
X to the 1 over 1 is literally just x. Okay. Okay, evaluating upper minus lower. So I have 3 to the 4th over 4. Plus 3. And then minus, let's see, -1 to the 4th over 4 plus -1. So it's 81 over 4 plus 3. 81 over 4 plus 3 minus 1/4 plus 1. So 80 over 4 is 20. 20 plus 4 is 24. Cool.
Wait, no.
No, because minus a -1. Minus a -1. Are you going to D? Okay. So if we were taking the derivative, we would subtract 1 on the exponent, but here we're going to add 1 to the exponent since we're taking the integral. So 3 over 2 plus 1 is 5 over 2.
Yeah.
So x to the 5 over 2, and instead of, and we divide by 5 over 2, dividing is the same thing as multiplying by 2/5. Yeah, instead of dividing by 5 over 2, we can multiply by the reciprocal, 2/5. Okay, so divide by 5 over 2, the same thing as multiplying by the reciprocal, 2/5. We're evaluating from 0 to 4. So this is 2/5 times 4 to the 5 seconds minus 2/5 times 0 to the 5 seconds. So keep in mind, 4 to the 5 halves is literally going to be the square root of 4 to the 5th power. The square root of 4 is 2 to the 5th power is 32. Okay. So 2/5 times 32, what? But, right, top dog is in the house. 5 is in the house. So you could say square root of 4 to the 5th, or you can say square root of 4 and then to the 5th power. I used that for my intermediate, top dog in the house, and they thought it was great. Yeah. They actually don't think it's great. They asked me to stop saying the word dog. So top dog in the house. Top dog. And they're like, can you not say it? Top dog.
The top one isn't in the house though.
So you can have square root of 4 to the 5th. That's the same thing as saying square root of 4 to the 5th power. Because it doesn't matter which part of the exponent you do first. You can take the square root and then to the 5th power, or you can do the 5th power and then square root. Okay, let's keep going. All right, let's do another. Exactly, we still have 2 minutes. Okay, let's do it. So, negative sine theta is the derivative of what function? What function, when you take the derivative, is going to be negative? All right, so it's just cosine. Cosine theta evaluated at pi over 6 and 5 pi over 6. This is just supposed to be, this should be like bread and butter now. This should be a nice, easy question because you studied cosine, sine, tangent in starting geometry and then algebra 2 and then pre-calculus and now this class, so I'm expecting you to know what it is.
Oh my god.
Wonderful. So,
One second. Okay.
yep.
So negative sine theta is cosine theta. Okay.
Because if you think about it, going this way is the antiderivative, right?
Yeah. Going the other way is just the derivative.
Right, if you take the derivative of cosine, you should get negative sine. So this is why I sometimes talk to you about this differently than other teachers would, because I try to make this as simple as possible, right? I approach this problem as saying negative sine theta is the derivative of what function, or what function, when you take the derivative, is negative sine theta. Because ideally, I don't want you to have to memorize 50 million things. Like, if you know the derivatives and you know them well, this shouldn't be too hard of a step. So clearly, we're going to have to finish the last 5-10 minutes of the lesson tomorrow, but do you want me to pass out the practice test now?
And then is tomorrow review day?
Tomorrow.
Yes. I don't want it. Can you practice test? I can just keep it for tomorrow.
I'm not gonna do it.
Okay. I do have some things to hand out though. My
What's percent?
oh,
I thought it was rocket, and then I thought it was pilot. It's like pilot bird. That's pretty good. Where's my phone? No, it's I'm being concerned.
Amy collection bar, quote, Amy quote chart and then her campaign. What?
Now it's only
And then Doris Joe Biden.
what is Bluebirds?
And her the South Force.
God, he was my name. I'm saying.
You know I'm voting.
Look, I did a percent. I did all my research for the judges. I know. No, you're doing Thank you. I stayed up for
Thank you, Anna.
What is this?
He's witty. He's also I know. So it's not like I have heart attack in the middle. He's calling him out, but
Oh.
ridiculous. I don't know why we're gonna elect someone who's not gonna be all like I don't know. Bye. I'm voting today after school. So. I know.